In the previous video, we have seen the bad news that achieving domain consistency for the circuit constraint was an NP-complete problem. Therefore, we need to find a relaxation. One possible relaxation to do the filtering for the circuit constraint is to do a reasoning based on the degree. As you know, the degree in a Hamiltonian circuit has some specific property. The set of edges that we'll select will form a circuit for which the in degree and the out degree of each vertex is exactly equal to 1. And so let me introduce first a notation there. I will denote like this the set of cities that have J as a possible successor. Okay, so for instance, here for the city 0, the one that have as possible successor 0 correspond to 1, 3, and 2. Okay, because all these ones, they are incident to node 0. So what we can already deduce to have a Hamiltonian circuit is that if you realize that one successor variable of your circuit constraint is fixed to some value j, so the successor of I is fixed to the value j, then you can remove j from the successor variables of all the other variables. That's exactly the same rule as the one that we have used for forward checking for the all different constraint. This one is not equivalent to the all different constraint. It says that if you realize that the incoming node into node j, okay, there is only one such node, which is the node I, then we know that the successor of node I has no choice to be equal to the node j. Okay, let's see how this one can be used to filter the situations there on this small example. So what we see is that the node 1 here, you see that the only possible node that you can come from here is node 3. Okay, so this only node 3 points direct to the node 1. As a consequence, we know that the successor of 3 must be assigned to node 1. Because if we don't do that, then we have no city that will be able to enter into node 1, and this is mandatory in the final Hamiltonian circuit. And so we can safely remove these two edges there. Okay, we know that these two edges will not be part of a solution to the Hamiltonian circuit on this graph. So in terms of implementation, for the first case, the first rule, so if we realize that one successor variable is fixed, then we can remove this city from the domain of the other variables. We can do exactly the same as we did for the forward checking algorithm of the all different constraint. That is, if you remember, you just split the set of variables in two, the ones that are already fixed, the ones that are not fixed, and you only need to consider the pruning on the unfixed set of variables to make it more efficient and more incremental. So you only consider the unfixed set of variables incrementally. This one is, you can do something that is quite similar. You need to count for each value j the number of successors that have j as part of their domains. That would require at least n squared to do that, but you can do it also a little bit more efficient, again using this same trick of splitting the set of the cities in two. So you will have the fixed and the unfixed ones, okay? And so you can use a sparse set for that, and you only to consider the values j, okay, and the variables I not yet in the fixed partition for the counting. Okay, and so if you do that, you can achieve the counting more efficiently. And once you realize that you have a count of exactly 1 for some city, you can fix the successor of the incoming variable that has this specific value j inside the domain. The degree-based filtering is a little bit weaker than the domain consistency for all different. Let's see why it's the case. So if you look at this example, you see that each city has at least an incoming degree of 2, and each city has an outgoing degree of at least 2. So clearly the degree-based reasoning rule that we have seen before cannot deduce anything on this example. But still, it's possible to deduce something. You see that the successor of 0 is 1 and 2, and the successor of 3 can also be 1 or 2. As a consequence, we note that 1 or 2 will be taken by the successor of 0 or 3, And so it cannot be used here. So this one, the value 2 cannot be used here, and the value 1 cannot be used in the successor of 2. And so we can remove these two edges. Because if you would do that, there is no possible solutions for which you have 1 and 2 that is still available for these two cities. Okay, so that illustrates that the degree-based reasoning is not enough, and we can do more by using the domain-consistent all different constraint. So, but still, the degree reasoning is faster to execute than the domain-consistent for the all different. This is why it's still used in practice, because you can achieve better performances in terms of efficiency of the speed, and so it's more scalable than computing the matching of the strongly connected components and so on. But the all different constraint, even if it's domain consistent, it's not enough. So with the all different constraint, even the domain consistent one, you cannot realize that you have two subtours, for instance. This is totally fine for the all different constraint. And as you can see, there is no solution for the circuit constraint. The all different constraint is not able to detect that. And so we need to have something else. We need to be able to prevent the creation of subtours. And so you only need to have one global circuit for the circuit constraint.